the regular languages and automata. So last time we have explained what is sigma star. Sigma star, and we have also explained the Klein star. One thing to understand is that you have a language, and the language is every trace that can be produced from the model. So the behavior of the model is actually a language, and the language is included in sigma star. For example, here you have the following traces, and these are all parts of the language of the model. So this is the same thing as we have drawn early on. And one thing to see is also you have every time you have a parallel, for example here. So I have the following trace, which is R. So this is R, C, A, P, then I, and then K. So when you have a parallelism here, you are actually adding two possibilities. So either here I'm going to have P and then I, or I'm going to have I and then P. And let's say you had another path in your parallelism. You had another. Now you're adding actually two more. So either you're going to start with P, then I, then the following, or you're gonna be starting with I, P, and then the other transition, or you're gonna start with this transition and then you go to this one and to this one. So all in all, every time you add the parallelism, you're adding more to your language, more to the possibilities of behavior of your model. So that's one thing. Also, if you have a loop, then your language is infinite. So if you have a loop, let's say you have AB on a loop, and you can repeat AB, you actually can do that in infinite ways, meaning that your language is infinite. L is infinite. So to describe your language, you need what we call a machine, or what we call here a DFA. DFA stands for deterministic finite automaton. So you have a trace. If you're gonna say that the trace belongs to a language, which is the description of the behavior of your model, you're gonna need this. So let's start. We have this machine. You have the circles here, each one of these circles. So here you have a circle, and each one of these circles is a state. These arrows are the transitions. And here, the green double circles are valid places to stop. So the idea here is that you're gonna run your trace from left to right. You're just gonna follow your arrows, of course. And for each activity, you're gonna follow, tack, 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 and then you're gonna see if you land on a valid end places or not. If you land on a valid end place, then the trace that is produced, let's say you start with RC, for example. Here, if I go R and then C, I'm not ending up in a valid end place. So it doesn't belong to the automata that we created from our model. And if we end in a valid end place, we're gonna say that it's belonging. So one thing to know, I'm just gonna go, let me build you the process step by step. You will understand why this diamond and why we have P and I. So let's start. We have R, C. So R is representative of receive, C is check, and here we're going in two ways. You're going either here or here. So if you go reject, that takes us directly to close. Here there is no problem. On the other hand, if I approve, here I go to this diamond. This diamond is what is represented by the parallelism early on. So either I'm gonna do P and then I, or I'm gonna do I and then P. So let's see how that looks like. For example, this is a valid path and we are ending up in a valid end place, so it's accepted. And as I told you early on, we cannot stop in the middle. You need to stop in these. So one thing to know is that you have what we call DFA and what we call a NFA. The DFA is deterministic. So this is DFA. It's deterministic. It has exactly one arrow per activity. So here you only have one arrow. and it's totally mechanical. So you're just following the arrow stack. On the other hand, the NFA you can branch. One thing to know is that you can actually convert every NFA to a DFA. The problem is that what would happen if you go from here to here, like from here to here, is that you will have an explosion of states. So that's a problem, but also for clarity, it could be nice to have a DFA, of course. Also, one thing to know is prefix automation. So it's a handy version. It accepts every partial order. So everything here will be a valid stop. It's what we use if you're checking a case that's still running, like in the mid-flight. So one thing to always remember to never make a mistake. Here, this is actually a state. It's not prepare shipment, or it's not. So the arrow is the activity or the transition here. What this actually means is that you're actually saying, it's like, okay, I've done receive, then check, then approve, and then I did one of the parallel steps, which is here, the P, and I still owe another step to close here, to get to Q6. So that's the description of Q4. That's what Q4 means. It's not really a description of, it's not a description of P or anything like that. This is a mistake that many people do. So this is something to always remember. So the way to see it is that you have a machine, you have a language that's of the model, and you have a language of the log. The language of the log is real life, is what happened in real life. And what you will do, what you're generally doing, is that you're running what happened in real life, your traces, and you're running them along the language of your model. So the language of your model, which is the machine. So let's see, for example, you have this trace. It's receive, check, approve, then P is ship, and I invoice, K close. So we follow, okay, R, I'm reaching a valid state here, Q1, then I'm following here, I'm finding Q2, then Q3, these are all valid states, and I'm ending up in a valid stop. So this is conforming. What we're doing here is conformance behavior. On the other hand, let's say I have this log. If I have this log, I'm trying to every step, so I'm starting from Q0, I'm doing the steps that are in the trace. So I'm trying to find a valid state after every event that's happening in the trace. So I'm going here from Q0 to Q1, no problem. I'm finding Q1, that's a valid state. Then I'm doing C, so that's C. I'm finding Q2, so no problem until now. Then A, I'm finding Q3, that's another valid state. Q4. Now the problem is that if I do K, I'm not finding a valid state. So here I'm seeing a deviation. So this is why I'm seeing a deviation. So here we're introducing a new concept. This new concept is complement. What is a complement? So the complement is every trace the model forbids. In a way, the mental image you need to have is the reverse of your own model. So let's say you have a DFA here. Your first step is that you're going to take from every non-valid stop. So these are your states which are not valid stops. And from them, you're going to create these transitions. These transitions. Yeah, these are transitions, but they are fake in a way. And they represent transitions that should have never happened. And this is a trap state. And this trap state, you're going to keep on looping. So once you come from Q1 or Q2, you come to this trap state, you're stuck there. You just keep on looping. So that's first step. Second step, you're just going to flip. So if you can see, every state here is flipped. Q1 is flipped. So you're flipping from this is a valid state, it goes to non-valid state. This is non-valid stop, becomes a valid stop. So you flip all of these. And the idea here is that you're going to create all the traces that the model forbids. So here we are introducing a new idea. So what we call precision gap. Precision gap is the language of the model if you remove from it the language of the log. Meaning that sometimes your model allows a lot of traces and you have your reality or your log. You have your log. And sometimes that gap between them, the gap between this and this, is very important to observe. So that's our new concept. So the point of all what we are doing is that sometimes you have syntax, like a finite description of states or conditions. For example, send invoice before close. That could mean lots of things. And another thing is that two descriptions, two syntaxes could have the same automata. So our goal and the reason why we always build automata, because it's more rigorous and you can find all the possible traces. And for LLMs, that's very valuable because LLMs botch like they sort of rely too much on vibes. They botch complements, interleaving, and equality. So building automata can bring them more context and stability. So one honest limitation is that these machines have finite memory. They cannot count without a limit. So saying, for example, exactly as many shipments as invoices, no matter how many they are, like the unbounded, an automaton cannot track that. And so processes with real unbounded counting are out of reach. For normal stuff, on the other hand, if you have a bit of parallelism, you have choices, or you have sequences, it's more than enough. So you need to know that there is this issue to know when to use them. So actually, you can build a machine in a declarative way. For example, you can say you have multiple rules, and each rule you can build a small machine. For example, here approve. If you approve, you have to close eventually. You can build it as a machine with two states, x0, y0, and this is the valid stop. Same thing for precedence. Send invoice before close. You can build it with a small machine too. This is a machine that represents this. Same with not coexistence, not both reject and approve. So all of these small machines, if you build the intersection with them, you can find your model actually. So it's like a stack of very small machines to create your bigger machine. So here, let's talk a little bit about code. First of all, we have the following function, which converts a Petri net and makes it one of the machines that we have been talking about. Then we have the following function, which is discover declare here, which takes our log and hands back a nested dictionary. And in this nested dictionary, so this is a dictionary. If you don't know what's a dictionary, check Python. Like this is one of the basics of Python. The idea from here is you're gonna build templates of relationships like precedence or response, and then the activities involved. So you have, for example, existence, you have receive order, for example, and then another activity, or so existence is on its own. Precedence needs two activities. And one thing to always know is that you have support and confidence. You have support and confidence. So support is how often the rule was relevant. Confidence is how often it actually held. So to go into I will not go into really deep details, but these are thresholds so you have a score for each of these activities, for each of these entries in your dictionary, and then you set a threshold of discovery for these activities. And then you have the last one, which is conformance declare. We have already discussed this in another video. And the idea is here, you're going to take your log and your model, and you're going to compare them. Is fit if you have fitness score at 1, you have number of violations, deviating constraints. So all of these are, in a way, you're building your conformance between your log and your model. So let's do a recap now. First of all, we discussed how a regular language represents behavior. Then we saw how a DFA and how that diamond represents concurrency and how a machine checks the membership of a trace into a model. Then we saw how circles represent progress and they are not activities. This is a very important point. They are not transitions. Then we saw how you have overlap between two machines and how you get conformance. We also saw how to build the complement, how you flip the two steps to build the complement. Then we saw how there is a difference between what's the syntax you have and how semantics and how automata bring certain rigor and they are auditable. Finally, we saw how to declare a model and how to stack all these little machines together to build the model machine. So if you liked my content, please follow me on LinkedIn, and like and subscribe.